Now to the main event. So we're going to hear about whales in the forecast. So this is going to be, this year we're going to do a tag team. We wanted to highlight our senior research scientists, but also members of the teams that they work with because they don't do it alone. So today we've got Nick Record. Many of you know Nick. He has been here since 2013. He has got degrees in mathematics, oceanography, physical oceanography, and his research is all about the future of the ocean. What does that future ocean look like? How can we define what it looks like? How can we define it on timescales that are useful to human beings? He also is an incredible writer. He's working on a book. So I hope at some point we will have a book opening here. No pressure, Nick. And you might have seen his work in Maine Boat Homes and Harbors, because he has pieces in there frequently. We are also joined by two postdocs, which you will hear. He will introduce them in more detail. But the first one is Rebekah Shunmugapandi, who is from India, and Jonathan Syme, who is from Australia. And I wanted to just say, one of the things that has kept the United States at the forefront of science and technology since World War II is we were the place that the best and the brightest of around the world dreamed of coming. And that's not true anymore. We've become a very scary place for a lot of foreign scientists to either come to meetings or to come and spend time to be trained or to spend their career here. And I think that's that scares me almost as much as anything else for our future, because climate change is bearing down on us. And our ability to deal with it is going to be the brains and the creativity of the people that will find solutions at all levels, and getting people of all walks of life involved in that activity from countries around the world. That's going to help us in so many ways. So we really need to support, and we really need to make sure that we're the country that's that city on the hill that scientists want them to come to. So with that, I'm going to turn it over to Nick Record.
Thanks, Deb. And thanks everybody for coming. It's kind of amazing to be here in this space. The first Café Sci talk. I almost feel like I'm not worthy. But if any of you have come to my Café Sci's before, you know that I like things like props and activities. So we're going to have all of that. We're going to figure out if a whale could fit in this room, and we have some things to pass around. So hopefully we'll break in the new facility and style. Like Deb said, I'm Nick. I've been here for about 12 years now. I direct a center called the Tandy Center for Ocean Forecasting, and we produce all kinds of different forecasts of the ocean, ranging from things like toxic algal blooms, which is used by the aquaculture industry here in Maine and also internationally, to help plan around when toxic blooms are happening. We have forecasts we do for like jellyfish. We have a lobster shell disease forecast project we're working on, and a variety of different things. So there's all kinds of different work going on in our group. Today we're going to talk about forecasting that we do for the North Atlantic right whale, also a really important species. It's mostly going to be Rebekah and John talking. I'm like Deb said, it's one of the things that's amazing about ocean science is that it's really collaborative and it's really global. The ocean, of course, has no borders. And so I'm really lucky to have some brilliant scientists working in my group here at Bigelow. And so I'll let them mostly talk about the science. But I do have a few slides just by way of introduction to get you oriented to right whales and some of the things that we're thinking about before I pass it over to them. Okay, so to start off, I first started studying right whales about 20 years ago. I had never seen them. I remember the first time I saw a right whale. We were out on a pretty small boat, and someone said, right whales, look, right whales. I'm looking around, I'm like, where? I don't see any right whales. And then I looked down, and I saw this amazing animal coming up from under the boat. And like the photo just doesn't do it justice. Like photos never do these things justice, but it really doesn't. And I know because when I showed this to my nephew, he was like, oh, is that a hippopotamus? I was like, no way. Like you could put a hippopotamus into its mouth, just to give you a sense of scale. And you can see like can you see the surface of the ocean just bending under its weight? Anyway, it's pretty amazing to see. If you ever get a chance to see a North Atlantic right whale, don't pass up that opportunity. There's only about 350 of them left. We'll talk more about that in a bit. And it was interesting thinking about, I'm going to talk for a minute about the history of like what brought me and that whale together on that particular day. And it was like a pretty formative day for me. So first, the history behind the whale. This is a map by a research group in Massachusetts who reconstructed the routes of whaling ships going through, well, you can see the date starting in the 1830s. Whaling began before that, but this is just the ship logs that they had access to. And what this brings home for me is this idea that whaling was really the first global big oil. The lights of the cities of the world were lit with whale oil. And it wasn't until fossil fuels were developed or discovered and so on until most of the whales of the world populations had been depleted, that we stopped hunting whales. And you can see like just the amount. So first they depleted the populations in the North Atlantic, and you can see all these vessels are going in and out of New England, Nantucket, and so on. And then they started moving to other parts of the world. And I show this map in my classes, and even just earlier I was talking with John about it, how you can see like, oh, one area gets used up and they move to Australia, and then they move to New Zealand, and so on. And there's some interesting patterns with the oceanography too that I talk about with my students. But it's just, think about all the extraction that's happening and this just transfer of wealth to the Northeast US, which is in some ways still with us. Anyway, the 1900s eventually come along. We won't play this all the way through. Attitudes changed. Partly it was the discovery of another source of oil, but and partly it was just the depletion of whales, but there were also a lot of successful changes in public sentiment around whales. And eventually there was the global whaling ban. And then in the US, later on in the 70s, we have the Endangered Species Act, and then following that, the Marine Mammal Protection Act, and then eventually the Right Whale Recovery Plan in the 90s. And so now we have all this legislation in place in the US and globally that has helped whales around the world recover. And actually lots and lots of whale populations are recovering in really positive ways. But we're not talking about lots and lots of whales. We're talking about the North Atlantic right whale. So let's take a closer look at what's been happening with that species. I told you there's about 350 of them left. That's probably a pretty accurate estimate. The species probably bottomed out around 100 individuals sometime in the mid-1900s. Those are genetic estimates. They weren't really surveyed at the time, and probably would have been hard to survey anyway at such low numbers. By the 90s, when the Right Whale Recovery Plan was put into place, there were about 261 by this estimate. And over the next 20 years, I started studying right whales in the early 2000s, right before that kind of sharp uptick that you see. So it was actually kind of a hopeful time. There were some management measures that were put into place, some sacrifices by some of the fisheries and shipping industries that helped quite a lot, and some changes in the oceanography, and the population recovered to almost 500 individuals. And then in 2010, the oceanography shifted, and John's going to talk about this a little bit later, but this is where we are today, like somewhere in the the population's now been declining for the past 15 years or so, and we're down in the mid 300s. That decline kicked off in 2010 with this unusual mortality event, like I said, connected to changes in the climate and the feeding conditions for whales. And we've been struggling to figure out how to manage in these changing conditions. I'm going to come back at the end after these talks, after John and Rebekah, and give you a little bit of sense of how management is done and some of the successes, but some of the things that it's struggling with right now. But one of the things that is really important, I've learned, is that when these different approaches to management start to crack and fall apart, there's a really important role for science to play. And I believe that some of the modeling and forecasting tools that we're developing can help turn the tide while the management has become really polarized and that sort of thing. I think some of these tools that John and Rebekah are working on will, we can sort of channel science to help improve the situation. So with that, I will conclude my introduction, and I'm going to pass it on to John.
Good evening, everyone. My name's Jonathan. I'm a postdoc here at Bigelow, and my work is looking at the response to climate change by the endangered North Atlantic right whale. Now, we all know that whales are big, but just how big is a right whale? Now, we could give you numbers and say that an adult can grow up to 16 meters or 50 feet. We thought maybe it's better if we can give you a visualization so you can see just how big that is. I'm going to get my two volunteers here. We're going to walk out 50 feet on this measuring tape. So you can imagine there's a whale here that is 50 feet long and over 75 tons. What is even more amazing is that this huge creature feeds on one of the world's smallest. This little critter is called Calanus. It's a crustacean. It's a relative of the lobsters and crabs, and it's only a few millimeters long. And we don't have to imagine how small they are because we actually have some here in jars. And I'm going to ask my assistants to come up again and pass these jars around. And as the talk goes on, have a look in the jars, see if you can see them. They're very small, and then pass the jars around. So this huge creature is eating these tiny little bugs. Now in this diagram, clearly the whale and the copepod, the Calanus, are not to scale. So if we want them to be to scale, we have to shrink the little Calanus down till it's just a speck that maybe you can see. And we also have to make the whale bigger, a lot bigger. So now that they're to scale, the whale is 5,000 times longer than the little things that it's eating. So hopefully this gives you a perspective of what it's like to be a whale in the ocean looking for these tiny food. It's the equivalent of a human looking for and eating a single grain of sugar. Now, of course, the whales are not eating these Calanus one at a time. They're eating hundreds of thousands in each mouthful. And to do this, they use their baleen, these plates hanging down from the upper jaw, to filter the water and get the Calanus out. And this filtering is very energetically costly. They swim forward with their mouth open and the water goes in. And so for a right whale, it's not worth its while to feed unless the Calanus form dense patches. And there are a few locations in the Northwest Atlantic where these patches tend to form. And you can see some of them in this map here. And these locations are known as foraging grounds or feeding grounds, and they're essential to the whale's survival. And I'm going to keep referring back to some of these locations throughout the talk. And we'll start by looking at what we can call historic foraging grounds. So this map shows sightings of right whales from 1993 to 2009. And we can see some of those feeding grounds that we mentioned in the previous slide. Look at Cape Cod Bay, for example, and the Bay of Fundy. And you'll notice that there are different colors. And that's because these sightings are colored by season. So sightings in winter are blue, in spring are green, in summer are yellow, and in autumn are orange. So the whales aren't in all these places at once. There's a seasonality to their movements. So some whales spend the winter down south in Florida and Georgia, and then they migrate up in spring. Others spend the winter in Cape Cod Bay, and they come out in the spring, move along to the Great South Channel, and then east along Georgia's bank. In the autumn, they go to Roseway Basin and then up to the Bay of Fundy. And then as winter returns, they come back through the central Gulf of Maine to Cape Cod Bay or to Florida. So in general, there's this anti-clockwise movement around the Gulf of Maine between these different foraging grounds. And now I'm just going to point out the Bay of Fundy, which I'll talk about a fair bit. So this was considered one of the key foraging grounds for right whales. And this is because of a cold, deep water current that comes down along the coast of Nova Scotia and wraps around into the Bay of Fundy. And this current brings these calanists with it. Now, as Nick mentioned, in recent years, things have changed. And you'll see this date, 2010, coincides with that population decline. So this map shows sightings from 2010 to 2023, and like before, they're colored by season. And you'll notice that there are a few differences from the previous map. If you look back at the Bay of Fundy, there are fewer sightings there. And we can see that on this graph that shows the number of whale sightings by year from 1993 to 2023. So there's a general decline there, with no sightings at all in the last few years. And this is in part due to that cold, deep water current that over these years has actually weakened. So it's bringing less food in. And as a result, the Bay of Fundy is no longer the vital foraging ground that it was before. And whales have had to look elsewhere for food. So in contrast, we can look at places like the Gulf of St. Lawrence in the north and southern New England, where now there are lots of sightings where there weren't before. So what is driving these changes, and what kind of changes can we expect to see in the future? These are the sort of questions that we're trying to answer. This is, I should have mentioned, a graph showing the sightings in southern New England increasing over time, with quite a sudden increase in the last few years. And one approach that we're using to answer these questions is species distribution modeling. So these are models of where and when whales are found. And basically, we take parameters like temperature, salinity, and water depth, and we see how they influence where the whales go and when they go there. One feature that makes our models a bit special is that we're also using data on the prey, on the calanists themselves, to see how that influences the whales' movements. And these models are all contributing to provide greater insight into the distribution of right whales, both in the present and in the future. I'm now going to describe some of the specific topics that we're working on. So the first is to model each region and each season separately to capture that seasonality and those movements that I talked about before. So we're dividing the Northwest Atlantic into different regions and into different seasons and making models for each of them, seeing which factors are driving right whale occurrence and how they differ. And this will help us understand why whale numbers are decreasing in the Bay of Fundy but increasing in the Gulf of St. Lawrence and southern New England. And this will give us a better understanding of past habitat shifts, like this one we've just seen, and also of potential habitat shifts that may happen in future. We're also working on forecasts of right whale occurrence at different timescales. So the first set of forecasts are long-term scales. So we're talking about forecasts of where whales might be in 5, 10, 20 years' time. And we end up with maps like this one. So this shows right whale habitat. In blue are areas that will become right whale habitat in the future. Areas in red are currently habitat that will be lost in the future, and yellow areas that are currently habitat and will still be habitat in the future. And this is based on data from 1990 to 2015, and this map is just for the month of June. And I chose this map of June, the month of June, because of something that happened a few weeks ago. So the title says it all. Endangered right whale observed swimming far off the Newfoundland coast on June 5th. And this is quite unusual. But where exactly did that whale occur? It was right there on that little bit of blue, on this area that we predicted would become right whale habitat. So this suggests that these predictions are becoming true, which validates the predictions and is also concerning because it's perhaps happening sooner than we expected. We're also working on forecasts at a seasonal scale. So where will the whales be in the next season? So next summer, next autumn. Now, how do we do this? This plot here shows measurements taken in the eastern Gulf of Maine, close to the seafloor. And on the y-axis, we have temperature from cold to warm, and on the x-axis, we have salinity from fresher to saltier. And you'll see that the points on the plot are years. And all of the years from 2003 to 2009, not all, most of the years are towards the bottom left. So that deep water was colder and fresher. And the years from 2010, when that change happened, they're towards the top right. So the deep water was warmer and saltier. And you can see 2024 there, and we'll come back to that in a second. So if we plot the sightings from those years, we can see if there's some sort of correlation. So in those years when the deep water was cold and fresh at the bottom in blue, and those years where the deep water was warmer and saltier at the top in red. And we can see some differences between where the whales are occurring. And once again, we can look at the Bay of Fundy, and we'll see that there are fewer sightings. There are fewer sightings in those red years, and that's also shown in this plot here. So what about last year? Now, if anyone can remember back to the map that had the sightings colored by a season, right whales are found in the Bay of Fundy in the autumn time, mostly in September and October. And this measurement is taken in May. So what we have is a measurement in May that correlates to right whale occurrence several months later. So this allows us to make a prediction. And last year we noticed that this deep water, for the first time in over 10 years, was back to being colder and fresher. You can see where 2024 is on that plot again. And we made a prediction that right whales might return to the Bay of Fundy. And what happened? There they were. And so now you might be asking what's going to happen this year. We have 2 yellow circles on the plot, and they were measurements taken by Bigelow Lab. And as you can see, the water this year is again colder and fresher. So we can expect the right whales will be back in the Bay of Fundy in this autumn. We'll have to wait to see. The final scale for our forecast is short term. So we're talking 7 to 10 days into the future. So just like you have a weather forecast that says what the probability of rain or clouds or sun is in the next few days, we can make maps that tell what is the probability of whale occurrence in the coming days. And these maps could be used by researchers and management in fisheries to inform their decisions. And that brings us to an end to the first half of our presentations. And feel free to ask any questions to me or to Nick. I'm not sure if the question went through the microphone, so I'll just repeat it. The question was, if we can predict with that specificity, could lobster fishermen use that information to decide when to put their gear? We wouldn't be telling anyone where to put their gear, but we can provide that information. Just as you have a weather forecast and you look at it and you decide, am I going to go out today? Am I going to take an umbrella? And you make the decision. We can provide that information, and then it's up to them to make the decision.
With the shift from the Bay of Fundy up to St. Lawrence, Nick had spoken earlier about the different protection in different areas. What kind of protection is there off Newfoundland and in that St. Lawrence area?
I'm not sure about Newfoundland. That was pretty far off the shelf, but in the Gulf of St. Lawrence, so following what they call the unusual mortality event that started in 2017, where whales started to die in large numbers, and many of those were in Canada. Both countries took their respective approaches to protective measures. In Canada, the federal government has a lot more power to act directly. I mean, maybe we might think of Canada as smaller somehow and less powerful, but that's not the case for the federal government. It's it's larger per capita, if you want to think of it that way, than what we have in the US. And they have a lot more top-down control on fisheries. So they took actions like, as soon as a right whale is spotted, they'll shut down a fishery and have people haul their gear. And of course, that would be much easier to do if you had a little bit of warning for a fishery, right? So going back to the first question, it's sometimes hard in wintertime for fishermen to get out there and pull their gear out. The Canadian government also shifted some of their fishing seasons. So a couple of times they shifted the crab season earlier and actually had icebreakers out there so they could get all the fishing in before when they expected the whales to arrive, which the previous year had been in June. So they're doing a lot. They have a different set of laws as well. Like we have different risk metrics that we have to hit than what they have to hit. And so there have also been, at least for a while, there were these bilateral talks happening, attempts to coordinate. It's really hard given the 2 different legal configurations that we have to totally be on the same page, but people were definitely trying to do that.
We've been asked a couple times online, do you know what is causing the Bay of Fundy to become colder and fresher in the last couple years?
Oh, yeah. So that's tied. So the current that John showed in his map is basically an offshoot of the Labrador Current, which is one of the major North Atlantic currents. Another one you might be familiar with is the Gulf Stream, which is bringing warm subtropical water up toward Maine. And the Labrador Current is bringing cold subarctic water. And they tend to intersect pretty close to Maine. And what we think is happening is as the Arctic warms, so the Arctic is one of the fastest warming areas. As the Arctic warms, it's changing the stratification, basically the way deep water. Now, trying to avoid getting too deep into the oceanography. But what happens in the Arctic is water cools and it sinks, and that drives a lot of the ocean currents around the North Atlantic and around the world even. And the warming has slowed that process from happening. And that's changed the path and the strength of the Labrador Current, which in turn has changed how it's supplying the Gulf of Maine with those colder waters and with the callousness that John showed. So it's basically a really complicated network of currents that traces back to what's happening in the Arctic.
Is there a lot of competition between different species of whales, and does that affect the levels of prey and the migration patterns?
Yeah, that's a great question. So
He's a budding marine scientist. That's
I
why
can
that was
tell.
a great question.
no, that's super interesting. So in the Gulf of Maine, right whale is pretty much the only whale that eats copepods. We have a few other species of whale here, like humpbacks and minkies. We have fin whales, occasionally sei whales, occasionally sperm whales. But with rare exceptions, they're not really eating copepods like callousness, which is the species that we've been focusing on. They're eating more like krill or small fish. So the right whale is kind of unique ecologically. It's the only species that serves that role in the food web in this part of the North Atlantic, which is another reason that there's value to making sure that it doesn't go extinct. The question is, why do they call it a right whale? And as far as people can tell, it's because it was the right whale to hunt. They are more slow moving than other species of whale. They don't sink as quickly after they're killed. And they don't tend to flee or fight back like some of the other whales would when whalers would hunt them. So lore is that name comes from them being the right whale to hunt. But now they're the right whale to save. So on that, I'll pass it over to Rebekah.
Hello, everyone. Thank you all for coming here today. I'm Rebekah. I'm a postdoctoral scientist at Wicklow. Following up on Nick's and Jonathan's talk about right whale and forecasting, I'm going to talk about how we use satellites and remote sensing to detect whale food, specifically callousness. So before we deep dive into satellites and callousness, I'm just going to start with very simple question right here. Before you all, what color is the ocean? We all know it's blue. It's obvious, right? But we call our planet a blue planet. We call our Earth, Mama Earth, a blue planet, right? So I'm going to tweak a question a bit here. So it's blue planet, but ocean is just blue? Because when you all go on a boat on a nice day, you might have noticed different shades of color. So these colors that you're seeing like bluish, greenish, brownish in color is not just colors. They are the clues. So these color clues tell us what's in the water, like phytoplankton, sediments, or organic matter in the water that actually changes colors. And that's what we detected using remote sensing. So remote sensing not just take up pretty pictures of Earth, actually they gives us clues and they actually measures the ocean color. So they give us continuous information of ocean color the entire globe on daily basis. And that's what we call it as like ocean color remote sensing. So past 2+ decades, we have been using ocean color remote sensing to study the tiny plant, the base of the food web. And recently, the ocean color remote sensing method got developed to study the zooplanktons, which we call it as zooplanet remote sensing. And so the ocean color remote sensing is literally climbing up the food chain. And these, like I mentioned earlier about ocean color gives us clues. So let's see how this tiny Calnus Finmarchicus gives us like ocean color clues, how they change the ocean color. So interesting thing about these Calnus, they have pigments. They have specifically axanthin pigment. In simple words, they are like striking red color. So when they are at the surface, they actually change the color. So you can see how dense zooplankton sample have its striking red color. So when they are at the surface, they influence the ocean color, and which is strong enough to get picked up by the satellite. So here's an example how the Calnus swarms get captured by the satellite, which is one of the first detected zooplankton detected using remote sensing off the coast Norwegian Sea. So this gives us the potential of using remote sensing to detect those whale food, which is cool. So I'm going to like move forward, like why it's important to use those remote sensing to detect Calnus in the Gulf of Maine. So Calnus is pretty much more in the Gulf of Maine, and the Gulf of Maine is one of the hotspot for Calnus. And John has mentioned how it's pretty much linked with right whale. There are like potential feeding grounds in the Gulf of Maine where the right whales actually get over the season here. And these right whales are like picky eaters. They love Calnus for no reason. I have never tasted coffee pot before. I don't know how it tastes like, but they find it more tastier. So they were like all around the Gulf of Maine to eat them. So we want to use the remote sensing methods to detect those whale food. And with that help, we'll be helped to monitor those right whale. So here's a first example of how the Calnus swarm in the Gulf of Maine looks like. So that white arrow is pointing out the Calnus swarm here. And this gives us a strong signal of Calnus at the surface get picked up by the satellite. And the white star is the field observation on the specific date where the high abundance of Calnus was recorded. So this gives us a confidence of how we can potentially use the satellite remote sensing to detect the whale food. So moving forward, so we detected it, and these strong signal aren't just individual copy pod, is a kind of fingerprint of axanthin signal that picked by the satellite. So we use ocean color remote sensing method to actually detect them and try to quantify them. So here's an example of how we actually detect those patches. And these are the surface Calnus concentration patches that we detect using ocean color remote sensing methods. So this gives us a potential of using ocean color remote sensing to detect those Calnus from space, which is cool. And these are kind of an improving method that we've been using to detect those using satellite. And let's see how we use those satellite data for like potential applications on right whale tracking and monitoring. So here I'm going to show you some real-time examples how we can potentially use those data. So here's an example where you're looking at a whale map, often people used by the researchers and decision makers to spot the right whales and other marine mammals. So on the particular day, there was a very high aggregation of right whale in the Bay of Fundy. When we pulled the satellite surface Calnus maps of the same day, we could see the same high abundance on the same day. So which pretty much coincide with the right whale presence and the high abundance Calnus. So here's one more example from aerial survey track report from Maine Department of Marine Science, where they often go on aerial and vessel surveys to collect those marine mammal data, specifically focusing on right whales. So here's one of the report where it showed on the specific day where the right whale aggregations are more in the Bay of Fundy, and follow on the same day when we pull the satellite Calnus map, which shows the high aggregation of Calnus as well on the same day. So this gives us a link of how this prey-predator relationships is happening. And we do have some of the limitations like the white layer data that you see is the data gaps due to cloud cover. But despite that, we were able to have a real-time tracking using satellite remote sensing, which is cool. So here, moving forward, I'm going to show you like how we potentially use those satellite data layer in decision making or like having a risk map. So here's an example which shows a right whale tag, which is red, which is all moving around, and the blue are the shipping lanes. So you can just see how this right whale movement often overlapped with the shipping lanes. It's increased the risk of ship strikes. So we need, and you can ask, like they are tagged, right? But the right whales aren't comfortable tagging. They are pretty much highly sensitive to tagging. So we need more alternative and advanced method to monitor and protect them. So for that, we could use a satellite remote sensing Calnus map. So when we know where the food is, we'll be able to predict where the right whales are likely to be. So here is the potential of like having a daily whale risk map made using like satellite Calnus data as a layer into it. So this prediction map, which shows the right whale sighting and the prediction over the time of the year where they are likely to be. So having those predictions of where the food is, so we'll be able to monitor the right whale movement, and it'll be easy for us to like have a chance, give them a chance to for the survival and having a less risk for them. So here, so for every right whale, every birth is a risk. So what we owe them is the foresight, not the hindsight. So I'll just pass it over to Nick for the few closure remarks.
Thanks, Rebekah. So I just wanted to say a few things before opening it up to questions again, just to give you a sense of I sort of alluded to how whales are managed and how the science fits in. So I just wanted to talk a bit about some more specifics about that. So at the Tandy Center, we try really hard to make sure that our forecasts and data products in general are designed in a way that matches what people need and how they can use them. So we work with a lot of different partners on this kind of thing, including the Maine Department of Marine Resources. We work with fisheries. We're starting to work with shipping. And we also work with the federal organization that attempts to manage right whales. The way that works since the right whale recovery plan or actually since the Marine Mammal Protection Act, is that there's this team of people called the Atlantic Large Whale Take Reduction Team that's convened by NOAA and by the National Marine Fisheries Service. This is a group of about 50 or 60 people. It includes members of the fishing industry and representatives of the fishing industry. It includes representatives from non-government organizations and conservation organizations. It includes people from local, state, and federal management. And it includes a handful of scientists. So I'm one of the people on that team. And they take all of these people and like put them in a hotel for a week or a few days and say, you all have to come to an agreement. We have to reduce risks of mortality, or TAKE. It's called the Atlantic Large Whale Take Reduction Team. So TAKE is a euphemism for accidentally killing a whale. And your goal is to reduce mortality by X%. And you all have to come to a consensus. It's a process based on consensus. And so you can imagine some people whose livelihood is fishing and other people who are coming from the conservation side might not always agree, although in a lot of ways they do often agree. But there are definitely some contentious conversations. And we come out of that process with advice to NOAA, a recommendation that they should take. And that process was behind a lot of the successes that I mentioned when you saw that kind of incline in the early 2000s. There were things like changes in fishing gear to make lines sink to the bottom more in a way that they wouldn't tangle whales. There were changes in shipping lanes to avoid areas where right whales would feed and aggregate. And a lot of that has become more challenging recently for two reasons. One is the changes in climate that John explained, so that a lot of the management we've been using assumed that whales would go to the same places at the same times every year. And now that things are changing from one year to the next, without these forecasting tools, we don't have a really good idea of everything has to be reactive to how the year is playing out. So one of the ways that we're hoping these forecasts will help is to give a sense before events unfold of where right whales are likely to go. And that doesn't necessarily mean pull your gear out of the water based on a forecast or something like that. But even just finding where whales are is a challenge. It's a big ocean. There's only 300 of them. And there are limited resources. It's expensive to fly a plane to look for whales or to take a boat. So that's one of the things that we're hoping these forecasts can do. Help get it heads up before whales show up in large numbers in an area so that we can have some planning in terms of what we do. The other thing that's happened recently is that this whole process has become more polarized, like a lot of things have. Over the last 10 years or so, the recommendations that have come out of this group have been taken up by NOAA or the National Marine Fisheries Service, and then they've been taken to court by both sides, by both the industry side and pulling in one direction and by the conservation side pulling in the other direction. And in both cases, those sides have won. So it's really hard for management to know what to do when whichever direction they go, hopefully it's a consensus-based and science-informed direction, but it just winds up in court. And then the most recent one, the judge made a ruling based on how uncertainty was interpreted in a model. So this judge is not a scientist or a mathematician or anything, but that was the reasoning that was used. So to me, it really highlights the important role of science in these conversations. And what we're finding is that when the politics cause things to grind to a halt, there's still utility for the types of tools that we're building. So for example, we're working with the Maine Department of Marine Resources now to build some of these real-time forecasting tools. They're out on the water with, they've redoubled their survey effort so that we can hopefully predict and know ahead of time, just like some of the questions we're alluding to. So that even though there isn't a specific management rule in place that says you have to get your gear out of the water or what have you, everybody on board, from management to the fishery to conservation, wants to avoid entangling whales. And so if they have this kind of information ahead of time, we can help be proactive. And so I think, I guess I'm just saying, as the situation becomes more polarized and politicized and it makes decision-making harder, I think there is still a role for better science to help in that scenario. And I'm really lucky to have these great postdocs in my lab advancing the science. I would never be able to do this without them. And they're bringing in some really brilliant ideas and new techniques that I wasn't even aware of. And just really lucky to be at a place like Bigelow and, of course, coastal Maine, where these kinds of collaborations could happen. So with that, I'll say thanks, and we'll open it up again for questions.
I have a question about the shipping lane conflicts. I'm here.
All I hear is the voice, so.
Yeah. A two-part question. This may sound kind of elementary, but anyway, I don't know anything. Can whales avoid ships? I mean, do they sense that they're getting close to one or one is coming or whatever? And then the second one, you made a reference to working with the shipping industry. So are there really controls over the shipping lanes and places they're required to avoid?
Yeah, those are great questions. In terms of whale sensing, whales use sound in the ocean quite a lot to navigate. One of the challenges with ships is the way sound propagates around a ship makes it appear that the most silent or safest place to be is in front of the ship. So it's very confusing for whales generally. It's hard for them to know exactly where the sound is coming from. There have been some experimental technologies where people have tried to develop devices that would specifically communicate to a whale where a ship, I'm a ship, avoid me, basically. I'm not sure exactly where the status of that research is, but that is something that has been explored. Yeah, and then in terms of working with the industry, so there's been efforts for, I guess, regulation and management on both the fisheries side and the shipping side, because those are the two sources of mortality. I would say on shipping, it's been much slower for regulations to take hold. There has been some legislation that's bounced around just over the last few years to impose speed restrictions. There are some speed restrictions already. Most of them are voluntary. So a lot of I think it has to do with just the influence of the shipping, and shipping is a major global industry. And as big as lobstering is in Maine, shipping is has much more influence. So most of the regulations or actions that have gone through for shipping have been voluntary. And I don't know where this current round of legislation is going to go. It might wind up still being voluntary. It's more speed restrictions, essentially. There is a cost for vessels, like to themselves, when they collide with a whale often. And so there's some appetite within the industry to develop these types of tools so that they themselves, for practical matters, in the absence of legislation, there's still a benefit to avoid whales. And so that's one way that we think we can work with the industry and build tools that could still be used. Personally, I still think there's a role for legislation. I think there are certain times and places where speed restrictions could be really beneficial.
As a follow-up to that, what's the percentage, as you look at the mortality of the whales, between strikes, that is contact with a ship, and being affected by ropes and traps and so on?
Yeah, so most of the whales in the population have scars from one or both of those. So I guess what I'm saying is there's a cumulative effect. A whale can be entangled and struck by a ship even multiple times throughout its life. And those all have health impacts. In terms of and so assigning like one or the other to the mortality could be really hard. And on top of that, about half of the whales that die, nobody ever actually sees. They're just no longer reported. So every whale in this population is tracked as an individual because they have unique markings on their face. They're called callosities. It's due to something called a tiny parasite called whale lice. But it's sort of like facial hair on humans, but each one is unique. So people are tracking every single individual whale in the population. And so some of the mortality is just a whale finally is no longer seen for a few years. And so in cases like that, it's hard to say. I am eventually going to come to answer your question. So, but in a lot of cases, it's really hard to say what the cause of mortality is. It is believed by most scientists who study this that every whale in the population dies due to one of those two factors. No whale in this population lives to old age and dies of what you might call natural causes. As far as the sources of mortalities that have been identified, it changes year to year, and we're working with small numbers, but they're roughly in equal proportion. So some years you might have 2/3 from one source and 1/3 from the other. But if you look back over the last 30 years, they're about even. And so when you want to reduce the number of whale mortalities, hopefully close to zero, you have to tackle both of those problems.
It's a two-part question. Do these whales move in pods at all, more than one?
Yes. So there's a mix of loners and whales moving together. I don't think of them like pods, like the way you might see a pod of dolphins all moving together. They tend to meander a bit more than that, but they aggregate in really large numbers, especially in feeding areas or in their calving grounds.
Okay,
But they also do often travel on their own. Many whales are seen just on their own.
the second question is, if there's so few, have they ever tried to tag any of them so they know their movements? I mean,
Generally, right whales are like sensitive to tagging because there are like two types of tags we could do, like implant on them, and also like we can stick it on the skin. So both the ways it was having more, they are reacting badly to them. And these sorts of tagging is kind of temporary. We could tag them only for a while, and we just don't want to like harm them by that. So that's what we are looking for, like more advanced or improved method to like forecast, model them, and having those satellites as a layer to just improve, to monitor them, and the way we could conserve them more.
Right. We had a question online, one for John and one for Rebekah. First was for John. With those forecasts that you're doing, what are some of the variables you're using, and do they differ for the short-term forecasts versus the long-term?
Yeah, okay, good question. So the variables that we use, there are some common ones like depth, distance to shore, sea surface temperature, salinity. We also look at other variables like the temperature at the bottom of the sea, we talked about before, with that deep water current, that can be very important. Also in our models, we're including prey layers. So that could be prey layers from Rebekah's work for the satellites. It could be prey layers based on someone going out and collecting and seeing how many of these prey species are in different locations around the Gulf of Maine and other places. So those are the sort of variables we use, and they tend to be the same between the models. What might differ is how exactly we measure those. So you could use a long-term average of sea surface temperature, or you could use sea surface temperature in one particular place at one particular time. And that'll reflect the scale of the forecast. So if we're talking about a forecast 50 years into the future, we're using climate predictions, which are averaged over months or years. If we're talking about a short-term forecast, we want a value that is in that instant to reflect the short-term nature of the forecast.
The question for Rebekah builds off of that. With all those different variables you're considering, how important is the prey layer? Do you have any sense of what proportion of the forecast reliability comes from calamus versus some of the other variables?
So when we use those decision-making risk map, I was like focusing only on the surface because there's a lot more risk for right whales at risk when they are at the surface. And there are a lot more chances they would be likely at the surface because they breathe like humans. They are mammals, so they are not like fish. So they stays at the surface more often for food. And having those satellite as a layer would help us to give a kind of continuous temporal and fine resolution information of those food. And through that, it would be an additional layer other than like temperature or like salinity or like favorable condition for them. So this layer would be an add-on potential layer to find them like where the movement is, and they are likely to be at the surface mostly.
I wanted to come back to what I think it was John was saying about how colder water was coinciding with greater whale sightings in certain areas. But if I understood you correctly, Nick, later you were saying that happened because of Arctic melt, which was adding, I guess, then more cold water. So that doesn't seem like a really good long-term solution for having more colder temperatures. So do I have that right? And if I do, what would be a more productive way, whether that's through legislation or other steps that we could take to bring ocean temperatures down?
I think you have the oceanography pretty much right, but there is some back and forth. So the melting doesn't just supply cold water to us. The Labrador Current was already bringing cold water. If anything, the warming in the Arctic has has weakened it and shifted it away from the Gulf of Maine. Although the last couple of years, we've had it come back. So I think there is the long-term trend, but there's also some back and forth year to year as that trend unfolds, which is the utility of the seasonal forecast. In terms of what we could legislate to bring ocean temperatures down, I mean, I hear some chuckles, but it's a really big question, which is probably why there were chuckles, and a hard one to answer. I mean, the main reason ocean temperatures are changing are because of greenhouse gases and the burning of fossil fuels. And without reducing that, you'd have to go into geoengineering, which is a really, I would say, a nascent science with a lot of risks associated. In my opinion, the best pathway has to do with shifting away from greenhouse gas producing energy into other sources of energy. That said, if we were to shift entirely today, there's still probably 30 to 40 years of warming already baked in because of the time lags, the rate at which climate processes unfold.
What is the is there, what's your best argument for why we should care about right whales? I mean, is there anything specific that we would lose? I mean, other than, diversity, we all like diversity, and, they're very cute animals. Is there anything specific that the repercussions that there would be if we lost them? And how urgent is the situation from where you sit?
Yeah, thank you for asking me that question. Somebody asked that in the practice talk as well, and I had meant to say something. So thanks for giving me that chance. So in terms of some of the reasons that right whales are important. So for one, whales are, they themselves are a carbon pool, a globally significant one. And as we think about the balance of carbon around the planet, losing whales is a major loss in that sense. And whales also transport carbon to the deep ocean where it can be stored away for a long time. They fertilize the surface of the ocean as well. So whales eat, they also poop, and their poop is all positively buoyant. So it basically brings nutrients to the surface of the ocean, which helps to stimulate the base of the food web. So that's an important ecological role. And then in addition to that, from a food web point of view, whales tend to stabilize the food web because they're long-lived. And so they can eat a lot in the good years and less in the bad years. And from a food web perspective, that tends to even out the ups and downs over years. So you find in systems that have a lot of those long-lived top predators that there's less fluctuation from year to year throughout the rest of the food web. So those are some of the positive things that whales contribute. And then right whales in particular, they don't have, like I was mentioning to that earlier question, they don't have a replacement species. There isn't another species that fills that ecological role in this part of the ocean. There are other similar, like there's the bowhead whale in the Arctic, which also eats Calanus and so on. There are other somewhat similar species in other parts of the world, but at least for us, there isn't really a replacement. So those are some reasons, I guess, that are maybe more pragmatic why somebody might care. They are also, like, from an economic point of view, there are whale watches and things like that that benefit from having whales around too. So I think there's a lot of reasons why. And, from the perspective of one of my Canadian colleagues is that if we lose right whales, we're just going to be having this same debate about the next whale in line. So if we don't figure this out, it's not like it just goes away. It's a microcosm of many, many other similar problems that we're trying to solve. And so a lot of the lessons that we're learning here apply to many of those types of problems. You had another, and how urgent is it? Yeah, because we have a lot of urgent things in our news feeds these days, don't we? I guess if we had a doomsday clock for right whales, I would say it's not quite as bad as it was 5 or 6 years ago. You know, I think people were really feeling like we were close to the midnight hour with tens of whales dying every year. And that's, you know, that's big in a population with only 100 reproducing females. Things have stabilized over the last 2 or 3 years. The population levels are roughly stable, and the calving rates are starting to pick back up again. They're not quite to their long-term average, but they're not down in the basement where they were. So, you know, I think, I'm not sure exactly how to quantify urgency. I think things are a little bit better, but I also think we can't take our eye off the ball, because that first decline happened because of these sudden climate shifts that we weren't ready for. And there's probably going to be more like that. And so hopefully that's where some of this predictive science can give us an edge where we didn't have one last time it happened.
We have a lot of people to thank. First, we're going to thank HM Payson, who has been sponsoring this event in the Café Size series for many years. And it just is wonderful to get so many people in. It's a big shot in the arm every year. It's like I woke up this morning, I was all psyched that we were going to have the building full of people. So thank you to HM Payson. We have so many board members and advisory board members in the room. If you will stand up, if you are on the board, we're on the board, on the advisory board, can you please stand up so we can give you huge rounds of applause? So we are not an enormous organization, so we really count on people with sometimes very specific expertise that we really could use the help, and we're so happy when people step up and serve on the board. So thank you very much for all of you. There are so many other donors in the room. If you have supported Bigelow at any level in the past, thank you, thank you, thank you, thank you. Okay, so this is just the first of 4. So next week, we've got Water, Health, and Humans, leveraging community partnerships to protect Maine's waterways. And that's Rachel Sipler, many of you know, fantastic speaker, and Robin Sleeth, who's one of our newest research scientists and is just a spectacular young scientist. The week after that, PFAS. These are the forever chemicals in Casco Bay, tracking the fate of forever chemicals on Maine's coast. And that's Christoph Apley, many of you know, and Hannah Sterling, a research technician that works with him. And then the last one, ocean epidemiology, tracking marine diseases to protect fisheries and ocean health. This is Dr. Maya Groner, Melissa Rocker, and Rain Yoshioka, who is also one of our newest research scientists. So I hope you will come back next week. And thank you so much for joining us tonight, and drive safe getting home.